introduction. So let's get right in. And I will be talking about typed interaction with session types. But first, let me quickly demonstrate how bad the situation is without session types. We'll be modeling a canteen with some strict rules. You as a customer walk in and have to proceed through sections in this order. First soups, then main dishes, then payment. You can get any number of soups and main dishes while supply lasts, but if an item runs out, you have to proceed to the next section. In payment section, you have to pay, and then you have to finish all your meals. Okay, let's get some code. First in vanilla Scala. This is our interface. Canteen has only one method, enter, which opens a session, and session then has methods for getting soup, getting main dish, and a method for paying, which also closes the session. Each of the food items has a method to consume it. All right, let's write a simple customer behavior on top of this interface. Our customer enters, gets a soup, gets main dish, pays, and eats both dishes. This looks quite straightforward, easy to read. What could possibly go wrong? Well, everything. Getting items in the wrong order. Asking for more items after paying. Leaving without paying. Wasting food, not eating your soup. Attempting to eat the same soup twice. And refusing to move down the line after you've been told that we ran out of soup. So all of these lead to either runtime errors or resource leaks. Now let's look at the other side of the interface, the provider of the canteen. The session needs to keep track of state, so it does so in a mutable variable, and the state is one of 4 possible options corresponding to the stage of interaction. Then each method has to check whether it is allowed in the current state, and if not, it throws an exception. And this repeats in all of the methods. Here's get main dish, also throwing exception, pay and close, throwing, handling, and throwing an exception. So it was pretty bad, right? Dealing with illegal state, runtime errors, resource leaks, and on top of that, how would we discover what the correct protocol of interaction was? We would have to study documentation, but it either does not exist or is vague and outdated. And even after we arrive at the correct usage of the interface, our code will remain fragile with respect to modifications, like anything that's not captured by the type system. So let's take a step that will move us in the right direction. Let's split up the session interface into multiple types, each corresponding to a stage of interaction, and each having only the relevant methods. Each method on an object of stage will return the next stage, at which point the original stage is considered consumed and can no longer be used. It's a property also known as linearity. Here's our new interface. In session, your only option is to proceed to soups. In section soup, you can either ask for soup or proceed. If you ask for soup, it's now up to the canteen whether they provide you with the soup and you stay in section soup, or you are moved to the main section. Main section is analogous, and in section payment, you have no other option than to pay, which also closes the session. Okay, here's the customer implementation. Notice how we adhere to the convention that each variable is used exactly once. These are some helper functions, but they as well, every variable exactly once. And this simple convention of linearity prevents us from violating the protocol. How? Let me illustrate. Say if we were not to pay, that would mean this section pay variable would remain unused, which is a violation of this linearity property. Or getting items in the wrong order would mean we consume section soup twice, once to even get to the main stage, and once when asking for soup. The other side of the interface, the provider, now every method is allowed to be called unless we have already consumed the object. But here we are trusting the client not to do that. We are trusting them to uphold linearity, which is not ideal. All right, we see that this single rule of linearity solves the problems. And it's even more robust with respect to modifications because linearity can be checked locally and does not break at a distance by someone making modification elsewhere in the code. Though it might be somewhat unclear what is subject to linearity and what can be used freely. However, there's this caveat here that it's all based on trust, and one defector can ruin it all. So, can we do better? Seems like linearity is the right idea, but could we enforce it prior to execution? And this is where my library, Libretto, comes in. So we know that Scala does not support linear types, but let's play with this idea of representing programs as values. Right? We first assemble a blueprint, and then later it is executed by the runtime. Similar to, say, the I/O monad, except in Libretto we want more. First, we want a true blueprint that is not something that has already captured live resources from a running program. And crucially, we want the data structure representing our programs to make nonlinear programs unrepresentable. What could the data structure look like? A free category, and with some additional operations, will do the job. Let's jump right into some Libretto code. The customer should look fairly reminiscent to what we saw before with just the convention of linearity, except this time we're assembling a mere blueprint. Nothing is executing yet. This funny asterisk between bars stands for a pair in Libretto. How do we assemble those blueprints? We use this lambda provided by Libretto. It takes an ordinary Scala function these are auxiliary expressions, and translates it to our representation of linear functions. Basically, it realizes the correspondence between linear lambda calculus and symmetric monoidal categories. What if this Scala function violates linearity? Then already this lambda throws an exception, which means we haven't even assembled the blueprint yet, so nothing could be executing yet. That's what I call assembly time error here. All right, so let's look at some of those violations of the protocol. Getting items in wrong order leads to consuming subsection twice, which is a violation of linearity, which we detect at assembly time. Not paying means unused variable, which is a linearity violation detected at assembly time. Not eating soup, or attempting to eat the soup twice are both linearity violations detected at assembly time. Okay, I have shown you some code that triggers assembly time errors. How do we catch them? All we need to do is to try to construct the blueprint. And if it succeeds, it's guaranteed to be linear by construction. Now, I haven't shown you what this type session was, how it was defined in Libretto. But in order to do that, we first need to do a quick tour of Libretto's types of interactions, aka session types. So our program interacts through its import and outport, which could be of the following types. Done is a simple signal traveling left to right. Val is a Scala value, also traveling left to right. In other formalizations of session types, you would mostly have two distinct types for sending a value and receiving a value. In Libretto, a val on the output means sending, val on the import means receiving. We can form pairs where the interaction takes place over both parts concurrently. And then we have producer choice, where the producer picks whether to produce the left side or the right side, and the consumer has to be ready to handle either one. Dual to that is consumer choice, where the consumer picks whether they want to consume the left part or the right part. They have to pick exactly one. And the producer has to be ready to produce either one. We have function objects, which are internal in the program, and these are also subject to linearity. That is, the function has to be used exactly once. And we use a standard technique for forming recursive types, also known as the type-level fixed-point combinator. Another important type constructor is inversion. Whatever the data flow is through A, in inverted A, it is exactly the opposite. So inverted done is a signal traveling now right to left. Inverted val, Scala value traveling right to left. It's like sending values against the direction of the arrow. Inverted pair is the same as inverting both sides. And we have the nice duality that producer choice, when inverted, becomes consumer choice and vice versa. Okay, we have now built up enough to define the protocol of our Canteen in Libretto types. Let's start with section soup. First, it is the customer's choice whether to ask for soup or proceed. And if they ask for soup, then it's now the provider's choice to either provide a soup and the customer stays in section soup, or the customer is moved to the main section. Libretto has built-in functions to work with all these types, like producer choice, consumer choice, recursive types. But we can define some helper functions with more friendly names. To get soup, we just unpack one level of recursive definition and choose the left side. To proceed to main dishes, we unpack one level of recursive definition and choose the right side. Here I'm using some point-free notation for composing functions, not using the lambda that we saw before. In order to produce section soup, we have to have blueprints for handling both options that are offered to the customer, and then we combine them using the built-in choice operation and wrap one level of this recursive definition. Section main is exactly analogous. Section payment here is just a function where the customer provides their payment card. The Canteen might do something with it, but always returns it back. And now we can define the session as just a type alias for section soup, because that's where the interaction starts and everything unfolds from there. Okay, we have accomplished the task of expressing the protocol of our Canteen in types. We still have time to show you the other side of this interface. We saw customer previously. Let's look at the provider. To provide a session, it suffices to provide section soup and wrap it as a session. And to provide section soup, we use our helper function from before and give it blueprints for both possible customer choices. If the customer asks for soup, this provider always responds with success and makes a new soup and calls itself recursively so that the customer stays in section soup. You might have noticed this done variable is used twice here. That looks like a violation of linearity. However, some types come with an ability to be duplicated, and this done signal is one of those. But the ability has to be witnessed by an instance of this cosemigroup type class. And we use this lambda.plus, which then inserts one duplication for each additional occurrence of the variable. Main section is exactly analogous. Notice how nowhere in this implementation of the provider do we need to handle a legal state as we had to before. Payment section, recall that we defined it as a function internal in the program, and we create those using this lambda.closure, also provided by Libretto. And the name should suggest that the function may now capture variables from the outer scope, as is the case here with the done variable. No handling of illegal state. And to wire it all up together, this blueprint method is like the main method of a Libretto application. It receives a signal to start and sends a signal once finished. The start signal here is passed to the provider, which produces a session, and session is then consumed by the customer. And there's some more code to issue a payment card and shred it at the end. But this is a Libretto application. All right, we saw that with Libretto we checked all the boxes. No illegal state handling, resource leaks avoided, runtime errors avoided, and since the protocol is now expressed in types, we enjoy the nice property that it guides us towards, the types guide us towards the correct usage of the interface. As anything that's kept track of by types, it is robust with respect to modifications, and there's no confusion what has to be used linearly and what not. Non-linear linearity is witnessed by a type class. But there's more in Libretto than what I have just talked about. It offers seamless concurrency that is not built on effects like spawning fibers or spawning actors. Streams are readily expressible using only the types that we have seen today. There in one line is a definition of a stream, basically just alternating consumer and producer choice. Since it's not a primitive, custom combinators are easy to write using existing built-in functions, and the implementations do not need to fall back to low-level effectful programming with queues or mutable references and so on. But you can use effects with Libretto. They just don't contaminate orthogonal concerns like concurrency or streams. Resource management is very simple when you have linearity. You avoid all the complexities of managing resource scopes. And last but not least, if your programs as values are not hidden behind opaque Scala functions, this opens a whole new world of possibilities what you can do with programs, and these are yet to be explored and exploited by Libretto. So please try it out. It's on GitHub. Explore with me. And yeah, please, if you don't ask your question now, discussions on GitHub are enabled, so please do ask there any question whatsoever. Thank you.